This video is presented to you by Physics for Students. To know more, please visit us at physicsforstudents.com.
A very warm welcome from Physics for Students. My name is Shaunak and I welcome you to this fresh series of lectures on differential geometry. Before I go ahead and start with this lecture, what I would like to explain to the viewers is that because differential geometry deals with a lot of abstract concepts, it sometimes becomes very difficult for us to visualize what those concepts are. So I have done the best to give the explanation, both terms in terms of visual explanations and mathematical explanations. So first, geometry is a part of mathematics that studies the shape of objects. Now, the name geometry actually comes from the Greek word geo, which means earth, and metria, which means measure. And in the dawn of mathematics, geometry was the science of measuring the earth, which has been very important all along the history, and it is hence one of the oldest branches of mathematics. If you have gone through my series of lectures on the history of differential geometry, you might have witnessed certain important geometers and how the entire arena of geometry started and it shaped. Now, what do we mean by shape? Now, shape is actually an external form or contour, that quality of a material on which it depends on constant relations of positions and proportionate distance among all the points composing its outline or its external surface, a particular variety of this quality. Hence, we can say that shape is a quality that depends on distances among all points of the object. Now, this implicitly what it says, that we talk about the shape of an object. We do not take into the consideration where it is located in a space. For example, a bottle's shape is the same whether it is in the rubbish bin or on a table or whatever it is, since the distances and positions among all points of the bottle do not change. As you can see right there on the screen, I've just given a very basic school level idea of what the geometrical shapes are all about. So we come back to the basic question, what is differential geometry? Well, as you all know, however, it is good to recap that differential geometry is the study of geometric properties using differential and integral calculus, although most of the time we use differential primarily. Now, what are the geometric properties all about? Now, geometric properties are properties that are solely of the geometric object, not of how it happens appearance in space. Now, these are properties that do not change under congruence. What I mean is that a function is a congruence of its preserved distances. Length is the most natural and simple geometric property. Thinking of all the properties that are preserved in two congruent triangles, for example, the length of size, the area, the angles between the size, the height, the symmetries and the rotation, all of this. In contrast, consider properties that are not preserved. For example, the slopes of the sides, what are coordinates of the vertices, orientation, etc. So these are basically what are called the geometric properties, and it has some relation obviously with topology, where we study the invariance properties under rotation, flipping, bending, etc. Things remains unchanged. Now, the obvious question is that why do we use calculus to study geometry? Now, to be able to study geometric objects that are not uniform, that could be the obvious answer. The geometry you learned in high school or we learned in high school was fine for studying objects which are made up of points, circles, lines, planes, but it is not good for studying any other objects. I mean to say those which are not made of those pieces. So in other words, anything that is made out of curves that vary in their curvature. Then in differential geometry, we tend to work with objects that do not have corners, so that we can take derivatives as much as we want, but we may work with objects with corners piece by piece much like working with a polyhedron using the tools of high school geometry. Now, before I go and we dive deep into this topic, this should be considered as the I would say the prima facie, the starting point of differential geometry, which we call parameterization of a curve. Now, in parameterization is generally a mathematical process. In mathematics, and more specifically in geometry, parameterization or parametrization, whatever you call, is a process of finding parametric equations of a curve, a surface, or more generally a manifold or a variety which is defined by an implicit equation. So to parameterize by itself means to express in terms of parameters. Now, for example, the position of a point that moves on a curve in a three-dimensional space is determined by the time needed to reach each point, right? When the starting point from a fixed origin, as you can see on the screen, if x, y and z are the coordinates of the point, the movement of it is thus described by a parametric equation. So for example, we take x equals to ft, y equals to gt, z equals to ht, and t is denoting parameter, or which is denoting time. Now on the right hand side of your screen, which you can see y equal to f of x, which is very common to all of us. Now we can write this into two terms, right? We can write it as this, where x equals to u of t, and we can write y equals to vt, right? So such a parametric equation completely determines the curve without the need of any interpretation of t as time, and this is thus called parametric equation of curve. Now these two equations, if we can write it in two forms, these are the two forms. Now note that they are both influenced by t, right? But the curves will have an orientation once it is parametrized. Now there can be a lot of answers of writing this. The easiest way is this. Suppose I like x equals to t, then y becomes this one. But there are other ways. For example, if we can write it in this way, and then we assume x equals to t, then y becomes this one, 2t square plus 1, right? So what I'm trying to tell you is that this parameterization, let me show you. Yeah. So this parameterization has an orientation that the original did not have, but the curves look the same. Let us take another example in the box below on your screen. If we take x equals to 2t, and then we take this and we take this. So what happens is that this red line, this one and this one, right, though both of them has a different parameterization of the same equation. So this is just to let you know what actually parameterization is. It's a mathematical process, and we can use them and interpret them, and it is called a parametric equation of the curve. We will come to this more as we go ahead in further lessons of this video. So just as I told you that it is not that it is one way, there are infinite many ways of parameterization. Now suppose that we called a parametric equations of t, we take x and y are continuous functions of t. Now over an interval, obviously I, the set of points x and y obtained as t varies over the interval I is called the graph of the parametric equations. So we say, for example, if x and y are continuous functions, t being an interval over I, then the equation becomes this: x equals to xt, y equals to yt, and these are called parametric equations, and t is definitely called the parameter. Note that what I am trying to tell you is that I am using the c to denote curve. Now in certain books of differential geometry, you might find a little bit italic, a bent kind of a c, which is a little bit italic one. Both of them are the same. I have just used the straight C in order to know the curve family, but it is nothing. It is the same one. So that is how it is. So now what we do is that we take a graph, right? What I am trying to tell you is that based out of the graph, this chart, we are going to create a graph. Now as you see, the first point on the graph corresponds to this, t equals to -2, which has coordinates this one, 1 and -3. And the last point corresponding to t equals to 3 has coordinates 6 and 7, right? So what happens as t progresses from -2 to 3, the point on the curve travels along a parabola. Here on the right hand side, blue one, it is the parabola. So the direction of the point moves is again called the orientation, and on the right hand side of the screen it is shown as indicated on the graph. So what I'm trying to tell you is that through this chart and putting in different values of t with xt and yt, how do we obtain a kind of a graph for this? So how can we define parameterization? Now, what I would like to tell you, different books have different notations, conventions. I have tried to make it as simple as I can for you. So don't get confused with these notations. What I can tell is that a parameterization of a curve is a map, for example, RT, which goes up to within the note the angular brackets given, xt and yt from a parameter of interval. So from a parameter interval R equals to AB to the plane. The functions, this one xt and yt, are called coordinate functions, right? These are called coordinate functions. The image of the parameterization is, the image that we form is called a parameterized curve in the plane or in the space, right? So in 3 dimensions the parameterization takes kind of this shape where we get x, y and z. This is one way of defining parameterization. However, there are other ways of defining, and we will go ahead and understand why we need those definitions. So now the thing is that so what we get over here is that if we get this kind of a equation, we get what is called a Lissajous curve. We get this kind of equation. Obviously you can understand we get a parabola. With this kind of an equation, what you get is an ellipse, right, with a major and a minor axis. And with this kind of an equation we get an helix. So these are the different forms of curve which emerges, right? Lissajous, parabola, ellipse and helix. Further as we move, we find that if a curve can move faster, as you can see the parameters 2t, so obviously it moves faster, and with this minus factor coming in, the curve actually moves slower. So the parameterization describes a curve in the plane. Examples are Lissajous curve, parabola, hyperbola, ellipse and helix, all of this what you have seen. Now, a parameterized curve in Euclidean space, what if we can define, it is some kind of a mapping. So let's see that. So this is another way of defining. So you see that was a different notation of defining a parameterized curve. I'm using a separate notation to define the same concept so that it becomes clear for you in the book or in your further study. If you see different kinds of notation, you don't get confused. So a parameterized curve, obviously we are dealing with the Euclidean space, is a mapping which is I mapping out to R of n, where I is an interval in the real line, and we use this notation. Now hold on, I'll just explain to you what this notation is all about. This notation emphasizes on this factor, which is alpha, sends each element of the interval I to a certain point in Rn. I repeat, alpha sends each element of the interval I to a certain point Rn. What we say is that alpha is of the class Ck, providing that it is k times continuously differentiable. Right, so we assume that alpha is continuous, and whenever we need to differentiate it, it will assume that alpha is differentiable up to how many orders, how many levels we need. Right, however, we are not going to follow this convention. This is a little bit, complex kind of a thing. We will follow a different convention, but in case you come across textbooks with this type of notation, you don't get confused. Now, there might be a question which is going on in your mind, that is, what is a differentiable function? Here is a note. A differentiable function f is a continuously differentiable if and only if, technically I should have written IFF, but anyway, if and only if f is of differentiable class C1, and you can also say that a continuously differentiable function f of x is a function whose derivative, obviously the first derivative function f prime x, is also continuous at the point. So it might be looking a little bit complex, but you can just assume this is what is a differentiable function. Now just take a note of this notation which I have shown using this alpha sign. Now you see, when I come to further this helix which I have shown earlier, I can explain this in terms of this. Now you can see what I'm trying to tell you is that this things becomes a little bit more compact and we can explain it. So obviously in 3 dimension I'm using R3. If I take a parabola, I can redefine this equation in this way, which is R2. Further I can take, okay, fine. So now this is something which I would like to explain a little bit. This figure 8 curve, which is takes the shape of an infinity, actually is called the Limacon of Girono, or the Limacon of Huygens, or a figure 8 curve, whatever you call, is a plane algebraic curve of degree 4 and of genus 0, and is a Limacon curve shaped like an infinity symbol. Now this person, Camille Christophe Girono, I don't know whether I'm making the French pronunciation correct or not. So Camille Christophe Girono, or maybe Girono, was a French mathematician, and the Limacon of Girono, or the figure 8 curve, was named after this person. He's the first person to work on, I think I read the book, is working particularly on I don't remember. It is primarily maybe because of tangent vectors that this figure 8 curve. So this is another sign, same figure 8 curve, and the cubic curve can also be explained on this. So these are just notations. These are just figures in order to let you know that the same notation of defining different types of curves can be used, and it can be used in further notations to explain those equations. Well, as I always do in each of my videos, that I just touch the basics of the concept so that it becomes easier for you. So just a very quick kind of a bird's eye view on the basic concepts on vector and norm, so that things becomes easier for you as we proceed. First, the length or norm or module of a vector which spans from v1 to vn or v2 is defined as this. This is the first. That now this double bar, don't get confused of what it is. We are trying to just mention the length or the norm. Now the second one, the distance between 2 points P and Q in the plane Rn in the module is the module of the difference, that is this one. So just a quick brush up. The third one, the scalar or dot product of two vectors, right, which is written in this, equals to u1 v1, u2 v2, and it goes up to vn. So just note that the dot product is often used using a comma over there, so you just note that, be careful on that, right? And v square can be v dot v, right? The fourth one, if we think that the vectors in Rn I'm so sorry. So the fourth one is the scalar product, or the it satisfies the standard basis, that is the dot product. So this is the comma, so I told you to be aware. So this is just to go again, so this is basically the dot product. The fifth one, now if we think that vectors in Rn satisfies as n by 1 matrices, then u dot v, so it comes up to this, and this one which you all know denotes the transpose, that is the opposite part of that. So this is another point we need to mention. The sixth one is, if A is a matrix and if we denote its column vectors a1 a2 going up to an, this is something which you do just get a hang on idea. You don't really have to pause down and take a note. These things I know that you already know. So it is a matrix notation. If it is written in column vectors, how do they look like? Now coming to seventh point, which is the scalar product. The scalar products u dot v, it looks like this. So I believe you know. Coming to the eighth point, the standard basis of Rn will be denoted by E1, E2, I mean to say the basis one, which you already know. So just note that EI is an n tuple of all the zeros with a 1 in the ith position, right? And I already have written. Okay, so is the n tuple of all zeros with ith position. So in R cube, the notation becomes ijk, and it's quite simple for you. On coming to the ninth point, which is a basis v1, v2, it is called orthonormal if this one, and you can see that this curly one, we call it as a Kronecker delta, which is quite common in relativity and other areas. So this del sub ij is a Kronecker delta, that is a function with two integer, entries I and j that takes the value of 0, and I have written on the right side that if I is not equal to j and 1, and if I equals to j. So it actually traces the value, just to tell you on the Kronecker delta part. Coming to the 10th point, which is this one. So if v1 and v2 is an orthonormal basis, and if u is any vector, then we can express u in terms of the basis, which is this expression. And I think that is quite common. You might have seen in tensors, and linear algebra in general deals with this. And a vector or cross product of two vectors u and v in general in R3 can be written as this, u multiplied by v. So these are just a few basics. We are just left with few points. Now this 12th point, what I would like to tell you is that I am just defining the general definition of differentiability as this one. Okay, so the most general part, it is a map of f ranging up from Rn to Rm, is differentiable at a point of P, is a member of U, and if exists as a linear function. What is most important in this definition is that this linear function, okay, so this is the so this is how it is. Now the linear map, this dfp, is called the derivative of f at p. This is called the derivative of f at p. So the matrix associated with this dfp, when we write in terms of the standard basis, is denoted as J. Just a convention, because it denotes the Jacobian matrix. It denotes the Jacobian matrix. We are just left with completing our brushing of the basics with two more important points. We call the isometries of the Euclidean space. In case we get M1 and M2 as two matrix space, and D1 and D2 be the respective matrix, we tell that mapping this one. So it is an isometry if this one is for all points P and Q, includes that of M1. And lastly, the orthogonal transformation of ARN is a linear map which preserves the inner product, this one. So that is more or less, I just noted down, these are the 14 points which are, there are more points than that. These are more or less an idea, a kind of an basic idea of what are the things that we need. Well, what is a curve? With differential geometry deals all about curves. So a curvy line, curved line, or just curve is a line obviously which is not straight. Now in simple terms, it can be any line, right, which is somewhat bent. Now ideally, based on mathematics, a curve needs to be continuous and smooth, we all know. So we get circles, ellipses, parabolas, hyperbolas, as well as arcs, sectors, segments, two-dimensional curves, shapes, anything. So various shapes such as spheres, cylinders, and cones are referred to as three-dimensional curved shapes. So we have simple curve, which we will deal later, non-simple curve, open, closed, downwards, upwards, whatnot. So these are just a basic definition of curves. Now, just to make a small note on that, if we get a kind of an equation or like this, for example, y equals to 2x minus 1, we get this kind, and we get this kind. Just to make you understand that all these notations can be represented in terms of the Cartesian equation, or say for example Cartesian coordinates, as f of x comma y equals to c. Here f is a function of x and y, and c is a constant. Just to tell you that this is basically a kind of a overall equation which these graphs or these figures can be depicted on. Now, from the point of view of a curve is a set of actually is a set of points. Now, this can be written something like this, right at the bottom of your screen. You can take a note, you can take a pause, and just state that if curve, I again denote C, that C is a curve is a set of points which is denoted by this equation. Now, these examples are all curves in the plane. Okay, again, yeah, here is a note. Again, that curly C. Just to make a note that you might see this was being replaced by this what you call this this red squared C. So don't get confused. It is the same, right? I'm using it for easier function. Now, all these actually are on the plane R2, but we can also consider curves in R3. For example, the x-axis in R3 is a straight line given by y equals to 0 and z equals to 0. So more generally, a curve in R3 might be defined by a pair of equations. So R3 is defined by xyz and xyz c1 and c2. Just to make you understand that curves of this kind, which you right now you can see on the screen, these are called level curves. Yeah, these are curves in the plane. These are called level curves. Now hold on for a minute. I'm just going to give you an idea why this is called a level curve, because the idea that the curve in these two equations, for example xy in the plane at which quantity f of xy reaches a level which is the c. Now let me take a moment here to explain to you what the level curves are and what is the utility. Now see, a level curve can be drawn by any function, right, which has got two variables. So here is a very basic definition of what is a level curve. You can just read it. However, in case we are looking for the representation for function of three variables, we have a level surface. From curve we go to a surface that helps us in the representation. So right, a level curve of a function is also defined as the curve of the points where the functions has constant values. It is very important. Now in simple sense, the level curve is simply a cross section of graph of functions, which when we do kind of an equation to some constant values. For example, a function of two variables, the values taken as x and y, then level curve of the points become bracket x comma y. Anyway, so one of the most common uses of this theory is what we call optimization problem. Now what do I mean by that? Now this can be done when the proper implementation of the theory and the value of implementation as well. So if we understand, say for example, with the help of an example according to the modern portfolio theory, if we have x and y that are used as instruments of investments, then their proportion of portfolio generates a contour that can be traced maybe by a circle or whatever. So in the subsequent process, as we increase the number in each investment, they can trace different levels, right, of circles in the x and y grid. This is one optimization problem in order to optimize a system or maybe investment, for example. Now again, moving from land to sea, we get level curves representing the high pressure and low pressure areas, and some are high pressure associated with dryness, sunny weather and settled conditions. Again, if the pressure level curves are close together, then we get wind and unsettled weather, something like that. Railways try to keep a level curve with inclines and descents normally as little as possible, and hence the need for tunnels, viaducts and bridges. Different contexts. Canals too try to keep level curves, and here we need a system of locks if we want to change and the level curve. So don't get confused. I just wanted to mention that these level curves helps in all those factors. Now for example, we get a path like this, right? Now what I'm trying to tell you, till now we have seen equations, right, x, y, f, all these plotting graphs, all these plotting curves, all these plotting figures. Now how about this kind of a curvilinear, a crazy kind of a stuff where we have got, and we start moving this. So here it goes, curls up, down and again and settles here, right? So this is a way to think about curves, which turns out to be more useful in many situations. So this is a curve which is viewed as the path traced by a moving point, in this case a red dot. So here it comes. Gamma t is the position of the point at a time. The curve is described by a function gamma of a scalar parameter t with vector values, whatever it is given, we will come to see. So we use this idea to give our first formal definition of a curve in Rn, which we are coming up. So before that, the scalar parameter t described by a function gamma, and gamma times t is the position of the point at a time t. So we come to the first definition, formal definition. A parameterized curve in Rn is a map gamma which takes alpha and beta and maps up to Rn for some alpha beta which ranges from minus infinity and it goes up to plus infinity, taking the variables greater than equals to alpha and beta. So a parameterized curve whose image is contained in a level curve C is called a parameterization part. So you see this alpha and beta actually denotes the open interval, which is this one, right? So a parameterized curve is whose image is contained in a level curve C, and it is called a parameterized part of C. So what you see is that I've just given an intuitional approach and understanding of this one. The purple one is a parameterized curve, and the level curve actually, which we have just seen with different kind of definitions, it is basically a shadow. I can call it is an image. Okay, let us consider it to be an image. That more makes things more technical. So it is an image of the parameterized curve. Now, for example, we get a kind of this parabola. So let us find a parameterization. So of this, so how do we find this parameterization? So what we do is that we take y equal to x square, and if gamma t equals to this, then gamma sub 1 and gamma sub 2 must satisfy this one, right? For some values of t which is part of alpha and beta. So for all the values of t in the interval alpha and beta, for gamma is defined, which we are yet to decide, ideally every point on the parabola should be equal to this one, right? So if we take gamma sub 1 t equal to 2 and gamma sub 2 equal to 2, we must take alpha beta, which would be ranging from minus to plus infinity, and we get finally into this, right? So this is the desired parameterization. You can just take a note how we have done this. So you can see that parabola, how do we have parameterized? But hold on. Remember, this is not the only way of parameterization of parabola. If we there are other ways. Now, for example, we can take this one, right, which goes up to t cube up to t6 with alpha beta coming from plus infinity to minus infinity. Another way is this one, 2t square 4t, and there are numerous other ways. Okay, it goes on and on and on, infinitely many other ways. So the parameterization of a given level curve is not unique. So this is the takeaway from this part. So we can use different kinds of parameterization, and it is this parameterization of level curve is not unique. So we can found few other more ways. Here is an example what is called an asteroid, which is almost looks like a star, and it has been studied by different geometers and men of eminence, D'Alembert, Leibniz. So we get a kind of a curve and an equation like this, and then we can take cos square t plus sine square t equals to 1, which we are trying to define for all t, and we get the x and y's value, and this one satisfied this, which equals to 1. So starting from Romer to Jean Bernoulli and going up to Leibniz and D'Alembert, this is a kind of again a parameterized curve, and this gives you all those equations which will make you understand, and you can deal with asteroids and asteroids into further details. Note one thing we are just missing out, so I just make a note. We should not forget right now that a function f which takes alpha beta and maps up to r is a smooth if the derivative, this one, exists for all n greater than equals to 2 for all t members of a and b, alpha and beta. So if ft and gt, right, if ft and gt are smooth functions, then what happens, you see, is wonderful. We get the results from the standard calculus. So we get the sum, we get the product, we get the quotient, and we get the composite, right? So this is just a note that when this function is mapping here and is a smooth if the derivative exists, and ft and gt are smooth functions, then what we get are the standard results of the calculus, the sum, product, quotient, and the composite one. Now in case, okay, let me go back here. Now in case if you want to take gamma t, right, and I want to differentiate component by component, I mean to say I want to differentiate component wise, so the components comes to gamma t 1 t, gamma 1 t, gamma 2 t up to gamma n t, then what we get is this, right? Now this is a cumbersome one, I understand, so in order to save space, time and everything, we denote this in order to get the first derivative and the second derivative. So we say that gamma is smooth if the derivatives of up to y exists for all n greater than equal to 1 and for all t is a member of alpha and beta, that is equivalent to requiring that the components goes from gamma 1, gamma 2 up to gamma n of gamma being smooth. Right. So there will be quite a few definitions about this. Don't worry, these definitions are actually very helpful. Now, the second definition that we come across is if gamma is a parameterized curve and its first derivative y prime t is called the tangent vector of gamma at the point of gamma t. So here we are again defining in terms of parameterized curve what is a tangent vector. So you see this is a kind of a graph that we see. So what you see, this point, which is the vector, actually is a parallel to the chord joining the points, right, of the image of C. Now just note here that, yeah, so this is one, I put a blue tick. So this is parallel to the chord joining the points gamma t plus del t. Now just note that as del t tends to 0, the length of the chord also tends to 0, right? So as del t tends to 0, the length of the chord also tends to 0, but we expect that the direction of the chord becomes parallel to that of the tangent to C at gamma t. So here is what I'm trying to tell you. The direction of the chord is same as the vector which tends this one. So we get dy and by d gamma dt as it tends to 0. So of course this only determines as well-defined direction tangent to the curve if dy dt is non-zero, and if that condition holds, we define the tangent line to C at a point P of C to be the straight line, which obviously I have not shown. So this is a kind of a definition which I have shown of a tangent vectors, and how that when del t tends to 0, the length of the chord also tends to 0, but because we expect that the direction of the chord becomes parallel to that of the tangent to C, right, at gamma t, but the direction of the chord is the same as the vector, so which tends dy and dt as del t tends towards 0. All those are fine, definitions and understanding of the concepts, but how about using them into practical purpose? Here is a simple example. I have taken a path gamma t, which is 3t plus 2t square minus 7 t minus t square, and we are trying to find a parameterization of the line gamma t at the point gamma 1. So what we do is that the line passes to the point this one, which is 5, 6, 6, 0. So we take a kind of a derivative of the path which gives the result d, this one, and when t equals to 1, obviously the vector becomes this, and the parameterization of the tangent line is this one. I'm not going ahead to explain how this is being done because this is quite evident from the simple rules of calculus, so I hope you can just look into it. Now this is something, a kind of a simple example, very simple, in order to let you know that how parameterization happens and how we can find parameterization in terms of certain given points. Well, the word is actually Limacon, which means the spiral cavity of the inner ear. This inner ear, if you see it, it's just due to its shape. Now, the earliest formal research on Limacons is generally attributed to Etienne Pascal, who was the father of Blaise Pascal. However, some insightful investigations regarding them has been undertaken by the German Renaissance artist Albrecht Dürer in his work Instruction of Measurement, which contains specific geometric methods for producing these curves Limacon, which we will see, and this it is named by Gilles de Roberval when it is used for an example in finding tangent lines. So here is an equation of a Limacon curve, and here it is how it looks like. I have taken this image from Wikipedia, and this is how the Limacon curve looks like. This is actually a parameterized curve which we will see, and it has got different variations. So this is the Limacon curve. We can take a spiral curve which is called a spiral Archimedes with the coordinate values. Then we can find a logarithmic spiral. I was actually going through finding out the arc length of logarithmic spiral. It seems to be too complex, so I just thought not to show it here. then we find something which is called a rose curve with r equal to 3 sine theta. These are actually, I won't say these are Limacon curves, but these are actually different types of shapes. So the spiral, the logarithmic, and the rose curve. Now you see that what I have done is that I have taken different values of r, 1.3, 1, 0.5, and cos theta, and you see the shape of the Limacon curve, how it has changed. And not only that, hold on, it also changed the way it has moved forward, and the x-axis, here it goes, the arrow, this arrow, this arrow, this arrow. So just try to show you, kind of a thing, that how it actually changes. And we can take a parameterized curve with this value, right, and we get a kind of a graph Limacon curve like this. Now here it is very important to note one thing. I think you have already noted, but it is just worth mentioning that do you see that gamma has a self intersection? So it has got a self intersection, the origin, in the sense that gamma t equals to 0 for t equals to 2 pi by 3 and for t equals to 4 pi by 3. Sorry, I'm so sorry. It would be 4 pi by, it won't be 4 pi by r, it would be 4 pi by 3. But anyway, so the tangent vector comes to this, right? So the tangent vectors actually comes to this part. And here it comes, we take the particularly y prime, the first derivative of y prime, and yeah, so it represents to this 2 pi and this one. So just my kind apologies. So t won't be equals to 2 pi by r, it would be 2 pi, it would be 2 pi by 3 and 4 pi by 3. My kind apologies. But anyway, the entire notion and the entire concept is it is here. Now if we take and continue with this parameterization, so you see that we see this, and it should be the same thing as a value of the curve parameter and not the value of this. Now this is something which I would like to draw your attention, that when we talk about a point, okay, the concept of a point of a parameterized curve, say for example gamma, so this should be the same thing, I mean to say the point, as a value of the curve parameter t, right, and not the corresponding geometric point gamma t, which includes rn, etc. So what do we get by this? Yeah, so now important thing is that now here I have made the right correction. It is 2 pi by 3. So although t is being well defined, you note that although t is being well defined, yet it is taking these two different values, right? So what is the takeaway, right? What is the takeaway? So just note that the curve parameter and the corresponding it should be the curve parameter t. So what is the takeaway? Let's see. This was the earlier definition, right? If gamma is parameterized, its first derivative is called the tangent vector. Now let us redefine that. Why? Because we have seen, in spite of t being defined, we are getting these two values. So what do? We redefine that. And how do we redefine? This is how. If gamma is a parameterized curve, its first derivative y prime t is called the tangent vector of gamma at the parameter value t, right? If gamma is a parameterized curve, its first derivative y prime t is called the tangent vector, fine, of gamma at the parameter value t. So it seems that to insist on this distinction, it takes away from the geometric point, but this error actually happens, that it takes different values of t, and we should redefine that definition with this definition, that same tangent vector of gamma at the parameter value of t. Now this is quite important, arc length and speed. Now let us see this kind of a graph, for example. It's a kind of a curvy graph, right? Now if we get this kind of an equation, for example, we have defined the curve as this. So and we consider the parametric equations something like this. So by arc length, what we do is that we add them. So obviously the answer is this. So we add it from t1 to t2 by the first derivative, and we do the same by squaring and getting the root. and also the length element becomes this. We will explain very shortly. So just to give you a kind of a what you call a basic definition of how to calculate or compute arc length. Now the distance between 2 points along a section of a curve. So you see I have just drawn it abruptly. What I'm trying to do over here is that this blue graph or this blue curve, I would say, I have used small lines, black, and just tried to add them up on an intuitional basis that this is the way in which we calculate the arc length, right? So approximation using Pythagoras' theorem, we get the straight lines, and arc length is defined as this, and in R2 function y equals to f of x, and if you put a value like this, then the Euclidean distance of the infinitesimal small segments turn to this, right? So this is just a kind of an intuitive understanding how we go ahead and calculate the arc length. Now we gotta get at this kind of, and you see that I have done the small lines in order to do. So if v, which goes from v1 v2, is a vector in Rn, right, and we so what we get is that, yeah, so its length is calculated as this. Now if suppose we get another vector, say for example v and u, right, so if u is another vector, right, so this is the length u minus v is of the straight line segment just in the points. So in order to find a formula for the length of a parameterized curve gamma, note that if dt is very small, right, let me show you, yeah, so if dt is very small, the part of the image of c of gamma between gamma t and gamma t plus del t, which is a slight increment, is also nearly a straight line, right? So it is given as this. This is very interesting point. And since del t is very small, okay, let me show you in this way, yeah. So since del t is very small, and we get this, which is approximately, I use this sign, approximately nearly equal to y prime t, so the length is approximately this one, right? So if you want to calculate the length of a not necessarily small part of C, the curve, we can divide it into segments, each of which corresponds to a small increment del t in t. Calculate the length of each segment using the earlier definition, this one, y prime t dt, and we can add up the results, letting del t tending towards 0, which more or less gives us the exact length. Coming to the next definition, so arc length, what it is, the arc length of a curve gamma starting at the point gamma t0 is the function st, which is given by this one. This is standard. I mean to say, it's nothing that I need to tell further, right? But in case we select, we start selecting different points. Now let me show you, yeah. So in case we select different points, which are this and this, then as by the constant, we get this, which equals to this big one. So you see that t prime 0 going up. This is a small kind of an integration. I think that things become much clearer. So if we had taken the different starting points in the resulting arc, which is this. So that's how. Okay, so how do we define a motion along a curve? Now you see that we have already seen that if t is the time, I mean to say the time of an object location, time, and an object's location is given by rt, then the derivative r prime t is the velocity vector of vt, which becomes obvious. So just as vt is a vector, right, is a vector which describes how rt changes, so v prime t also is a vector which describes how vt changes, which means this one is an accelerating vector or an acceleration vector. So this is how I mean to say we are defining motion along a curve. Now how do we parameterize it by motion? Step number one, we go for a step-by-step approach. So let us first imagine that we start moving the red circle. Here it goes up and down and up and down and up, right? Okay, so this is how the red circle moves. So we are imagining an object moving along the curve C. Let us suppose that RT, this one, is the position of the object at time t, right? The velocity of the object of time t is this, right? The speed of the object at time t is this, clear? The distance traveled by the object at time 0 to any time, it can be any time, is this, and we have this, ds equal to v t dt, right? So this is what is called parameterizing by motion on a kind of a step-by-step approach, a relatively simple example which becomes clear to you. Now I have taken this from MIT OpenCourseWare. This is very interesting and a very simple example. So this figure on the left hand side of your screen shows a curve, right, and a small displacement delta r, which I've shown as a vector with an arrow. So the length along the curve from the start to end is the displacement delta s. So what we find from here is that delta s is more or less equals to this, which leads to this, which leads, if for example the limit of delta t tending towards 0 gives us this. Okay, so quick and a simple example, visually you can understand what it is. Now we take a kind of a abrupt graph like this, just to show you an example. So we get this kind of an equation, and it is given by et cos t e sin t, right? And then we get this, and further we get this, and we get this. So this is just a quick example, that in case you are thinking that what would be an example of a non-trivial unit speed curve, right? So if we get this and we try to solve one, we can later check out those equations. So this is, a kind of a very basic, very simple equation on, what we call is that what is a non-trivial. We will come to this unit speed curve later, but this is just a quick example. Now in here I would just like to take a pause. It leads to a theorem right now, but we are not going to explain the theorem, just have an idea. So unit speed curves are parameterized by arc length from some value t0, right? Conversely, any regular curve x has a unit speed parameterization. This is a theorem. We can go ahead and prove that, but it's out of the scope of the video. We have other topics to cover. So this is just theorem. Now we come to a definition. Let us see that it is a parameterized curve, and say for example if this one is a parameterized curve, its speed at the point gamma t is this gamma prime t. So why I'm again redefining parameterized curve? Because I'm using a different notation. Why I'm using a different notation? So that you don't get confused when you consult differential geometry other books. And gamma is said to be a unit speed curve if gamma t is a unit vector and this condition, right? This is again a definition using a gamma. Now just note that a dot product or a scalar product of vectors a ranging from a1 to n, b going from this, is given by this. We know that. And if a and b are smooth functions, if a and b are smooth functions of a parameter t, then what happens is that we use the product formula. So yeah, here it is, to find this. So we use the simple product formula. This follows from the definition of the dot product and the usual product for formula for scalar functions, which is this. So just as you see how we move ahead with a and b as smooth functions, we are using and we are getting the product rule. Now, re-parameterization is it is an extremely important concept in differential geometry. Why? Because the geometric quantities which are associated to different curves, they do not change under re-parameterization. Again, we will start with a different kind of a notation. So you see, from parameterization, we are moving to re-parameterization. So if I take x as the parameterized factor, then obviously the re-parameterized would be x prime or something. Just in the way in general theory or special relativity, we move from a primed frame of reference to an unprimed, from unprimed to a primed frame of reference. Same kind of a concept we use here. We will use two different notations so that you don't get confused for that. So we say that beta is a re-parameterization. So this is a re-parameterization of the original one, which is this, provided obviously there exists a smooth bijection, right, which is this one, theta I to j, such that this one. So what we can say that this diagram, that means it commutes, right? The meaning of this is that if you closely look into this diagram, it means that it commutes, right? So we have shown it in that way. So this is one kind of a definition of re-parameterization. We come to the next one. So a parameterized curve, I have used tilde, right? Gamma tilde of Rn is a re-parameterization of a parameterized. Just be very careful which one is re-parameterized and which one is parameterized. So the top one is a re-parameterization of a parameterized curve, this one. Obviously there will be a smooth bijective map. If there is a smooth bijective map, this one, the re-parameterization map we can call it, such that the inverse map, this one is the inverse, is also smooth. Obviously if this is smooth, then the inverse will also be smooth. The inverse map is also smooth, and this one is true for all t prime, I would say t tilde, going into alpha tilde to beta tilde. Now that since phi has a smooth inverse, gamma is a re-parameterization. Okay, yeah, so gamma is also phi is a smooth inverse, so gamma is also a re-parameterization of gamma tilde, and yeah, this will be also true for all t. So the two curves that are re-parameterizations of each other have the same image, so they should have the same geometric properties. This is what is important. I repeat, two curves that are re-parameterizations of each other have the same image, so that they should have same geometric properties. Again, a quick example of re-parameterization. How can we re-parameterize this one? 2t comma r sine 2t by its arc length given from this to this. Okay, so first let us find that we consider 2t equals to 0, which implies t equals to 0, and if t equals to 0, then r sine 0 equals to 0 and r cos 0 equals to 3. Both of them is obviously true. So this happens at t equals to 0, and we try to find out s of t, which is this one. We plug in the values of s of t and we get this, further this, and further this, and we get this, and further solving we get s equals to, yeah, so we get this kind of a value. So we can solve t for that, and we can get t as this, and we can plug in now this rt factor, and we get the final answer as this. Right, so this completes more or less of today's lecture on differential geometry. We covered a lot of concepts, mathematical, and tried to explain them intuitionally. So what I would do is that in the next video I will try to prove these two propositions you can call any re-parameterization of a regular curve is always regular. A parameterized curve has a unit speed re-parameterization if and only if it is regular. Obviously we need to explore what is a regular curve and what are closed curves and further details on that. That would be the factor of my next video. Do let me know how you liked it. Please do like, subscribe and comment, and feel free to communicate with me at my email ID and the comment section below. Thank you very much for watching this video. Stay safe, stay happy, and have a nice weekend ahead. Bye.